Hi, I'm Cameron Motts. You see me at such fine quality educational videos as Drama in Chemistry? Who would have known? And is there more to chemistry and choir than they both begin with the letter CH? Okay, at the request of one of my students, I was asked to, hey, could you do something on oxidation reduction? And I said, okay, sure, why not? So here it is. Oxidation reduction, the idea, in a chemical equation, in a chemical reaction, electrons are going to be let go and electrons will be picked up. So they're going to shuffle around a little bit, and sometimes electrons will go off and do other things, and we can get into biology and all that, which we're not doing that. We're here to look at the chemical approach. So in oxidation, you lose electrons. Reduction, you gain electrons. Now there's a couple of ways to remember that. I call them mnemonics. One is Leo, the lion goes grrr. Okay, I could sit there and say, Leo, the lion goes grrr. Or losing electrons, oxidation, gaining electrons, reduction. Oh, isn't that a nice one? Now that's how I remembered it. But there is another way. If it's easier for some people, there's oil rig. Oil rig means oxidation is losing, reduction is gaining. Yeah, so Leo the lion goes grrr or oil rig, doesn't matter, whatever helps you, because you're the one who needs to understand this stuff, right? Now, you may hear another term called redox. This is it right here. All that it is an abbreviation of the two words reduction and oxidation. We kind of squeezed it together to get redox. Reduction, oxidation. So if you hear the term redox equations, or we need to balance out redox equations, guess what? It's talking about oxidation reduction. All right, on to solving a problem. We're going to do first one in an acid solution, okay? And I'll probably do a second video that will focus on a basic solution more than anything else here. So in an acid solution, and you'll understand that we're going to need to do that for this. So here's NO2 minus plus MnO4 minus gets us NO3 minus plus Mn2 plus. Great. You'd say, hey, it's not balanced. We're not worried about that right now. So we need to break it down into half reactions. Well, wait a minute. What do you mean by half reactions? Well, the idea about the half reactions, we're only focusing on the part of the reactant and the part of the product that they are directly related. So for example, NO2 minus goes into NO3 minus. Now, what in the world's happened? Do you notice something here? Well, hey, NO3 picked up an extra oxygen, but the charge is still the same. But has the charge in the nitrogen changed from going from NO2 to NO3? If you answered yes, congratulations, you're right. Now let's check this out. If we know our basic rules of assigning charges, each oxygen atom is -2. So 2 times -2 is -4. Oh, I'm so glad I can remember math. Now we got a -1 charge overall. So that means if this is a -4, then this nitrogen has to be a +3. Okay, we got that. We got the 3. Now over here, 3 times -2 is -6. But you have an overall -1 charge. So that means this has to be a +5. So this goes from a +3 to a +5. So I'm going to go ahead. Yes, you're going to need to know this. Okay? You need to figure that out. Okay. Now let's take a look here at our MNs, our MnO4s. Because this is going to be really, really important for us later on. So here's MnO4. Again, each oxygen is -2, and we got a total charge of -1. So 4 times -2 is -8. You get a -1 charge overall. That means this has got to be a 7 plus. See how useful that math is? Now here, it's an Mn2 plus. Okay, that's a no-brainer. Now, what happened? What happened to the nitrogen? Did it gain electrons or did it lose electrons? It lost electrons. Guess what? It's oxidized, because Leo the lion goes grrr, oil. Over here on the Mn, you may notice, hey, it picked up electrons. Wait a minute. Grrr. Yeah, gaining electrons is reduction, or the rig. Reduction is gaining. Okay? This is going to be a fairly important idea as we're moving onward here. Okay. Well, the first thing we need to do here in our equation is we're going to have to balance out the oxygens. We got to add water so we can make the number of oxygen atoms equal. You'd say, wait a minute, why don't you add O2 or O3 or just simply O's by themselves? It doesn't work that way. Because remember, you are in an acidic solution, so you're going to be adding water. And water is pretty universal as a compound out there. Yes, we do depend on oxygen, and we do depend on O3 for the ozone and the sun and all that, but for here, we need to add water. So, here we have 3 oxygens, here we have 2. Deficit. This side needs an extra oxygen. Guess where it's coming from? The water, right here. So we're going to add a water, just 1, that's all we need, we're not greedy. So H2O plus NO2 with the minus gets us NO3 with a minus. And that's it. Fantastic. So, what about the MnO4? Well, we have 4 oxygens here, no oxygens here, so we're going to be adding 4. Quattro, water molecules on this side here. So we can have 4 oxygens here, 4 oxygens here. Then of course the next question is, hey, we got all these hydrogens. Chill, we're going to take care of it. That's our next thing. We're going to be adding hydrogens on both. Okay, so we're going to balance for the hydrogen ions in both half reactions. So you notice there's 2 hydrogens here in this 1 lone H2O, no hydrogens here. Bam! We're adding 2 hydrogens here, just like that. We're good. Now let's look at the other half reaction that we have here. And here we have 4 H2O, so 4 times 2, 8 hydrogens. We have 0 hydrogens here, so we need to add 8 hydrogens in there. Okay? That would be kind of an important thing, ladies and gentlemen. Okay. We have the oxygens balanced, we have our hydrogens balanced, we have our nitrogens balanced, we have our manganese balanced. What else can we balance? Electrons. That's the next thing. And this is where we talked about earlier. See these oxidation numbers? They're going to kind of come in a little bit handy for us because they're going to tell us which side of the equation we need to add the electrons to. And here we go. So we know originally that this was a +3 charge. We know this was a +5 charge. Now, we have to add electrons to the more positive side. This is the more positive side because it's got a +5 compared to a +3. Well, wait a minute, you got a positive over here. Right, but this is more positive. So we need to add the electrons to make it equal with the positive on the other side, if that's the case. So, from +5 to +3, that means we need to add 2 electrons. Bam, check, we got it. Now let's take a look down here for our other one. Okay, let's look down here. Let's look at this one, and you may notice here is our Mn, and it happens to have a charge of a 2+. Over here, what's the charge on the Mn? Remember, oxygen's a -2, so -2 times 4 is -8, but you have an overall charge of -1. So this one has got to be a +7. Remember, manganese is a transition metal, so it can have multiple personalities. Seriously, it can. like some of the others out there. Remember, a large part of the periodic table, you have transition metals, and they can exist in more than one oxidation state. Right. Okay. Yay, we got all this. But now, remember, in order to make the reaction work the right way, we've got the same number of oxygens, same number of hydrogens, but we got to make the electrons the same too. We have to be fair about this. So that means we're going to have to multiply by factors so that the electrons on both sides are equal to each other. Now, we have, how many electrons on the left side here? 5. How many electrons do we have on the right side, the product side? 2. What number does 5 and 2 go into evenly? When in doubt, just multiply the numbers together and you have it. Well, let's see. 5 and 2, they don't go into each other directly evenly, but if you multiply them, 10. Yes, 10. They can. So guess what? We can do some stuff with this. We can work with this, and I'm going to have to make this a little bit smaller. So that means when we're looking at this, okay, and I got to figure out which color am I going to use for this, because I don't have a fuchsia. I don't have any, so this whole thing here, ladies and gentlemen, will be multiplied by 2. Because 2 times 5 is 10. This whole thing here is going to be multiplied by 5. This is getting a little messy, isn't it? But remember, we're working with our half reactions. Okay? And the idea is to make the electrons equal to each other. And I got to pay attention to my timing. Okay. Okay, time for me now to pick a color and stick with it. So we multiply all this stuff out. Here's what we're going to get. And I'm going to go and write this in black, because this is going to be a long one, so I'm going to have to write kind of tiny here. So here we go. We have 5H2O plus 5NO2 with a minus charge plus 10 electrons plus 16 hydrogens, okay, plus 2MnO4 minus. And that's going to result in, and I'm going to have to do it, I'm going to have to do this on the bottom, okay? So the red is going to be the product. You'd say, wait a minute, where did those 16 hydrogens come from? Remember, you're combining the two half reactions together, okay? So you have the two. You are multiplying 2 times 8, that's 16. 2 times 5 is 10. 2 times 1, 2 times 1, 2 times 4. Just like here, 2 times 2, 2 times 1, 2 times 1. Oh, sorry, not 2. I'm sorry, what am I doing? 5 times 1, 5 times 1, 5 times 1, 5 times 2, and then 5 times 2. So we have a lot of electrons and a lot of multiplication to do. So that's why I'm writing this down. It's all in one fantastic mess. 5NO3 minus plus 10 hydrogens plus 10 electrons plus 2Mn with a plus 2 plus 8H2O. Oh my gosh. Yes, exactly. This is an oh my gosh moment. What do we do next? Guess what? We are going to have to go ahead and start canceling out stuff. Okay? Well, wait a minute. What do you mean by canceling out? Look. I have 10 electrons in the product side and 10 electrons on the reactant side. Guess what? They're going to cancel each other out because they're on opposite sides, right? If my head is the dividing line, let me move here, and I've got 5 electrons here, 5 electrons here, guess what? They cancel each other out. That's the idea. So I'm going to go ahead And with some form, I'm going to take green. And I'm going to rub out the 10 here. Ooh, yeah, that's it. So, wow. Look at that. We just canceled out a bunch of things here. Okay, now, so what else can I cancel out? Well, I could cancel out the waters, couldn't I? I could cancel out the waters. Now, I got 5 here, and I have got 8 over here. Are they going to cancel out completely? No. Which side is going to have more waters? The reactant side, because there's more of it. This is 1 to 1. So, I'm going to have 5 waters taken out here. And over here, this is not going to be 8 anymore. No, it's not. What it's going to be, here's what it's going to be. It is now going to be a 3. Ooh, yup. Ooh. Now, what else? Is there anything else I need to worry about here? Oh, hey, guess what? Huh? Oh, I've got 16 hydrogens here and 10 hydrogens here. Are they going to cancel each other out completely? Nope, but they're going to go trying. And guess what? We're going to take out 10 of these bad boys, and we can cancel that out, and oh, look. We can cancel out 10 of those, so we have 6 hydrogens left. Woo, man, what a mess, I tell you, homeboys and homegirls. So let's take a look at this. Let's finally write out this mess so we can finally balance this. Okay, so 5NO2 minus plus 6H plus 2MnO4 minus is going to result in 5NO3 minus plus 2Mn2 plus 3H2O. That's it, boys and girls. That is a balanced redox reaction in an acidic solution because we used hydrogens and we used water. And remember, the hydrogens would be a clue. This is it. This is how you balance it, ladies and gentlemen. Key things, some key things to look at when you're going through. All right? You do your half reactions. You figure out what are the charges here on the main things. Not the oxygens. We don't care about that. But look at your main elements here. All right? Not worried about the hydrogen or the oxygen or the water. Could care less. Okay? Then, ladies and gentlemen, we go ahead and we're going to add water to account for the oxygens. All right? Then, to account for the hydrogens, we add hydrogens in both half reactions to eliminate that need. Then we need to balance for the charges. What charges are we talking about? The charges on the nitrogen and the charges on the manganese, the main serious parts. Okay? So it's not, you're not trying to cancel out the charges of the hydrogens, you're trying to cancel out the charges here. Okay? Because they're the players. They're the ones that make the difference. So then after that, you're going to multiply both sides by whatever factor, both half reactions by a factor of electrons that they both have something in common, like 2 and 5 is 10. Okay? Then you combine it into one combined mess. And then you start canceling out what's happening on both sides of the arrow. You're canceling that they're opposite. So if there's the same number on opposite sides of the arrow, you can eliminate it very easily. If you have more of something on one side of the arrow, then erase what's on the opposite side and take that number and cut down on that. Okay, especially for the water, we had like 5 waters here, we had 8 waters here, and notice we eliminated the 8 and we made it into a 3 because we eliminated 5 here and we took out 5 here. And then, ladies and gentlemen, this is our balanced redox reaction in an acidic solution. Woo! I am done! I'm Cameron Motz, and I'm here to tell you, redox is here to stay. Ciao.